So, what I want to discuss now is another interpretation of probability, where probability is considered as the rules of probability are essentially tell you how you should extend formal logic, the way you make deductions in formal logic, to statements that are not necessarily true or false, but that can a certain degree of plausibility. Okay, and indeed, most of the statements that we discuss about are never absolutely true or false, or very rarely they are absolutely true or false. In many cases, they can be true with a certain probability. And what we want to do is to have a disciplined way of arguing about the plausibility of these statements. Okay? So, for example, typical example is that we observe a phenomenon, then we have a theory, which is a mathematical model maybe of this phenomenon, and then of course the way in which we can understand whether this phenomenon, whether this model is correct or not, is to look at what are the predictions that this model makes on other phenomena that we can observe. And so, for example, in this case, you will have a theory, which is A, that predicts some other phenomena B. These are the prediction of the theory. Now, what you are really interested in is to understand what is the plausibility of your theory. So what you can do is to see whether your prediction actually are verified by experiments. So if you do this, if you show that B is true, this can only tell you that A will be more likely, or that BA is not necessarily wrong. But it can never tell you that your theory is true. Okay? And indeed, this is why science is mostly about falsifiability, producing a theory that have falsifiable prediction, so that we can show that our theory are eventually wrong, okay? Or we can gain more confidence in our theory by showing that they stand a lot of experimental checks, okay? Okay, so so then in order to derive this probability theory as an extension of logic, well, let's start from logic. Well, logic is about logical deductions. So the typical example is that if you have the typical deduction in logic is what is called a syllogism. And say, for example, an example is that if humans are all mortals, so every human is in a set of all things that are mortal, and if Socrates is a human, then you can deduce that Socrates is also immortal. Okay? So this is the typical way in which you have a statement that all humans are mortal, another statement that tells you that Socrates is a human, and then from this you can deduce, make a deduction that Socrates is also immortal. Okay. Now, this, you realize that well, this way of making deduction is only applicable in a very particular case where the statements that you are considering are in this type of very special relation. Okay. So what instead we want to develop, and actually here I'm essentially following the discussion in a book of James, and which essentially draws on the work of many other people, such as Polya, Robert Cox, etc., etc. So what I want to show, what James shows, is that essentially you can think of probability as deriving from some postulates that we want an intelligent being to respect in order to make reasoning or quantitative assessment about the plausibility of statements. Okay? So imagine that we want to design a robot, and we want this robot to make deductions on plausibility of statement, and we want to set out what are the rules that this robot should follow. So this theory is what you would call a normative theory that specify what are the norms that one should follow. Okay, so what are these rules? Okay, so first element is that the plausibility of any statement A depends on the state of knowledge. So depend on what is known, what does the robot knows, and we will call it C. C is the set of statements that the robot knows to be true. Okay? So given what the robot knows to be true, then we want to the robot to be able to attach a number to think about what is the plausibility of an event A. So everything should be a function of A given C. Okay. So the second statement is that we want is plausibility should be a real function. Okay, so we will call it G of A and C is the plausibility of A given C. We want this to be a real number, in the sense that we want to have a scale of plausibility. So notice that I'm talking about plausibility, I'm not talking about probability intentionally, because what I want to show is that by applying some rules on how one should argue about the plausibility of statements, then you can define for any way in which you define this plausibility, then what we will see is that if the plausibility satisfies these rules, then you can always define a probability that satisfies the rules that allow you to compute the probability of everything. Okay. So, we want the plausibility to be a real function, and then we want it to be in agreement with common sense. Okay. So agreement with common sense is it's essentially that, say, whatever is logic should be contained into as a special case of how the plausibilities are assigned, but also say, for example, that if you have if A given C is more likely than most plausible than A given C prime, then we want that the negation of A, so the not A given C, should be less plausible than the negation of A given C prime. So this is just in agreement with common knowledge. Or if you have that this is true, and then you add another information that actually is equally likely, is equally plausible under C or C prime, then this should not, so we should have, if this statement B is equally plausible under C and under C prime, then this cannot change the way in which we reason about the plausibility of A under BC or BC prime, because essentially this is an information that is not adding anything on the plausibility. Okay, so and then we want consistency, so that our way to compute the plausibility should be consistent. Consistency means that if we can reach a result through different way of reasoning, then the result should not depend on the way we do the reasoning. Okay? Every way of reaching a conclusion should lead to the same conclusion, because otherwise you could have a contradiction. Okay? Also, consistency means that there is all the information, all the knowledge that is in C is taken into account. I mean, there is no part of the information that is arbitrarily neglected. Okay? And also, it means that, say, if you have two events And your state of knowledge does not allow you to distinguish these or two statements, and your state of knowledge does not allow you to distinguish between them, then the plausibility must be the same. So, for example, imagine that you are throwing a dice, which have, say, 6 faces, and you can think of the statement that the dice will end up on a 1 or on a 6. And C is the statement that describes what is the dice. And imagine that this tells you that this is a fair dice. Okay. So given the statement about that describes the dice does not tell you anything about whether any outcome will turn out 1 or 6. So the probability of these two should be the same. Okay. If instead, for example, in the knowledge that you have, it was you knew that your dice is biased in some way, then this will not be true. Okay, so very good. Now, as I told you, so our strategy would be to define, in terms of this plausibility, a function. So what we want to do is to define a function of the plausibility. So we want to define a probability as a particular function of the plausibility, or to show that anyhow, in any way in which you define this G, you can always define a probability, a function P that satisfies the certain rules of probability, and the only rules that are necessary are essentially the product rule, that is that the probability of AB given C is equal to the probability of A given B and C times the probability of B given C. And the second thing is the sum rule, or indeed the probability that the negation of A given C is 1 minus the probability of A given C. So once you have these two statements, once you establish these two results, once you show that there is a function of the plausibility that satisfies these two rules, then essentially you can compute the probability of any other statement using these two rules. So for example, so let me show so let's consider the probability of the statement that either A or B are true. And here I'm using a plus and not a union, because I'm talking about statements and not about sets or subsets of a bigger set. So just to clarify this distinction, I'm using a different notation. Also, this notation for the product, this should be the intersection, but I'm just using the product here. Okay. Okay. So how do we compute this? So we can compute this if we use the sum rule there. This is 1 minus the probability of A plus B, the negation of A plus B. But now, what is A plus B is the statement that neither A nor B occur. So this is just the product of A, negation of A times the negation of B. Okay? So then this is just 1 minus the probability of A times probability of B given C. And well, I can write this as 1 minus the probability of A given C times the probability of B given A and C, using the product rule. Okay. Now, again, using the sum rule, I can write this as 1 minus the probability, 1 minus 1 minus the probability of A and C times 1 minus the probability of B and A and C. Okay, and sorry. And so if I expand this, I have that there is 1 minus 1, then there is probability of A given C, and then there is the probability, there is this term minus is minus, there is plus, yes, 1 minus B of AC times B of B given AC. Now this is the probability of, this is 1 minus BAC is the probability of A bar given C. So this times this, this can also be rewritten as the probability of A given C plus the probability of A, B given C. But this is the probability of A given C plus now AB, this yes, this is plus the probability of B given C times the probability of A given B and C. Okay. But now you can use again the sum rule, and because this is 1 minus the probability of A given B and C, then you see that this one gives you P of A plus P of B, and this one gives you P of B given C times P of A given BC, which is exactly which gives you exactly the P of A given C plus P of B given C minus P of AB given C. Okay, so I mean this calculation is a little bit lengthy, but it shows you that you can for every combined event, if you have, you can relate this probability to the probability of other events. Okay, and these are exactly the same rules of probability that applies that we have seen in Kolmogorov axioms. Okay. Okay. So now what remains to be done is to show this, is to prove that the product rule and the sum rule are a consequence of these postulates on how we should make our reasoning. Okay? So let's start with the product rule. And the first idea of the product rule is that if we think about the plausibility of a statement that A and B are true given a certain state of knowledge, then we want this to be a function only of the plausibility of A given B, C, or and the plausibility of B given C. Okay, so or equivalently, there should be a function of the plausibility of A given C and the plausibility of B given A and C. Okay, because this is the way in which we argue about the plausibility of A and B. So first we argue about the plausibility of one of the statements given what we know, and then about the plausibility of the other statement about the other statement and what we know. Okay, so the fact that the plausibility of statement A, B is only a function of these two things reflects common sense, reflects our way of making reasoning, okay, about logical statements. And also, for example, so for example, we don't think that the plausibility of A given B and C should matter at all in the calculation of this, okay? Because, if B is not true, if we know that B is not true, then AB is not true. It's not going to be true. So that then this cannot tell us anything. So the plausibility of A, given that B is not true, cannot tell us anything about the plausibility of AB given C. Okay. Okay. So if we take this assumption, then essentially we can think of computing so finding out what this function might be. But first of all, we think that this function as a function of two arguments should be increasing in both. Okay, so if plausibility of B given C increases, then this will make the plausibility of AB given C also increase. Okay, and the same for this. And then let us think about a little bit more complex example. So let's think about the plausibility of three events A, B, C being true given state of knowledge D. And I can write this in two ways. It's a function of A given B, C, D times the plausibility of BC given D times the plausibility of BC given D, and then I can write this as plausibility of A given B, C, D, and F of G of B given C, D times G of C given D. But I can also argue in another way. So, for example, I could ask what is the plausibility of CD or let's say or AB given CD time and the possibility of C given D. Okay, and if I again use this this equation here, then this would be f of A of G of A given B, C, D, and G of B given C, D, and G of C given D. Okay? Now you have two expressions. So this one and this one, and they must be equal. So you see that here you have the function f that depends on the same arguments. Okay, so if we call this x, we call this y, and we call this z. Then this equality here tells us that the function f should satisfy the following equation, which is that f, sorry, let me write, f of x and f of y and z must be equal to f of x and y and z. Okay? So we end up with this equation plus the condition that f must be an increasing function of both of its arguments. And then one can look at what is the possible solution to this equation. So what are the solutions for f of this equation, of this functional equation? And this is a problem that has been studied a lot by mathematicians. And what is has been shown is that the function f of x and y, so this equation, the condition that f should be increasing, imply that f of x must have this form, which is the inverse of a function w computed in wx times wy, where wx must be an increasing function of x. So this tells you that w of f of x and y is equal to w of x times w of y. Okay, so if you apply this to this equation, it tells you that w of g of so of f of x and y, which is equal to this, of g of b, c, See, so if you apply the function w to this equation here, then you have w times w to the minus 1 of this, which is just essentially equal to w of the first argument, which is g of a, b, c, times w of the second argument, which is this, which is w of g of a and c. So what you see is that now you can define a function. If you define a function gamma of w as so if you define this as just gamma of a given bc, then you find that this function gamma, which is w applied to your definition of plausibility, then should satisfy this equation that is the gamma of, sorry, this is AB given C. So this is, I'm applying W to this equation here, so this is G of AB given C. So you find that gamma of AB given C should be equal to gamma of A given BC times gamma of B given C. Okay? So which is essentially a product rule. Okay? Okay, so which is very similar to this one. Okay, so the consequence of this is quite interesting because so let's analyze two particular cases. So let's imagine the case where the event, so the statement B is actually true, or say better, statement B given C is true. Okay. So then essentially AB given C is equal, because B is true given C, then this is just equal to A given C. And likewise, say B C is just equal to C, because B is true given C, B is implied by C, so essentially BC is equal to C. So then if you take this equation here, then this tells you that gamma of A given C, which is this, must be equal to gamma of A given C times gamma of B given C. So for if this equation has to be true for every statement A, then this means that gamma of B given C must be equal to 1. So every true statement, for every true statement, the value of gamma should be equal to 1. Okay? Now, let us now instead take a different situation, where instead let's assume that the statement A is false. okay, of A given C is false. Okay, so if this is true, then AB given C is also false, and it is essentially equal to A given C. Okay, then also the plausibility of A given B and C. So if both B and C are true, and A is false given B, then A will also be false given given B and C. So the plausibility of A given B, C, if A is false given C, then it must also it must be the same. Okay. So the plausibility of a false statement, if you add more information, essentially remains a statement which is false. If you add more information, then remains false. Okay, once the condition for it to be false are specified. So if you apply this to this equation, what you see is that, well, again, you have gamma of A, C, which is this, because AB given C is equal to A given C. So the plausibility of a false statement must be equal to plausibility of false statement times gamma of B, C. This should be true for any B. Okay, so but in order for this equation to be true for any gamma, then you should have that the plausibility of this function of the plausibility of a false statement must be equal to 0. So this implies that gamma of A given C must be equal to 0. So what we have found is that so this function gamma, which is defined in this way, tells you that if you have a true statement, then the function gamma of this true statement must be equal to 1. And if you have a false statement, then the function gamma of this false statement must be equal to 0. Okay? Very good. So let us now go to the sum rule. The second rule. So for the second rule, what we want to show is, now let's work directly with this function gamma. We want to find out how do we relate this function gamma of the negation of a statement to the function gamma itself, to the function gamma of the statement itself. And of course, there must be a function that relates these two. Again, by common sense. Because if a statement becomes more plausible, then its negation becomes less plausible by the same amount, okay, because it's just a negation. And okay, so now what we want to do is to find out what this function s of x must be. Okay, from what we said before, if we have a true statement, then so if A B is true, then gamma of A B must be equal to 1. So we have, and of course, the negation of A must be false, and gamma of A B must be equal to 0. So this tells you that S of 1 must be equal to 0. And if you revert A if you revert this, if you say that A given B must be false, then this must be true, then you also get that S of 0 must be equal to 1. Okay? And also we think that this function should be a monotonous function between these two limits. So these are the two extreme limits. So for any statement A and any state of knowledge B, then this should be the plausibility of a statement which is neither certain nor impossible. It should be between 0 and 1, and this S should also be between 0 and 1, okay? Because these are the two extremes. Okay, so now we can derive an equation for this S by the following argument. So let's compute the function gamma for AB given C. Now this is equal to gamma of A given C plus gamma of B given AC. Now I can write this as gamma of A given C times the function S of gamma of B given AC, and I can rewrite this as gamma of A given C times S of, now this thing I can write it as gamma of A B given C divided by gamma of A given C. Because by the product rule, gamma this times gamma of A given C is equal to this. Okay? Oh, very good. So now I can also do the same argument, the same derivation as here, but just interchange B with A. And then I get another equation, which is gamma of, say, A, B, and C divided by gamma of B given C. Now, the idea, so this is an equation that relates, that if you take this equation here, is an equation that for this function S. Now, the idea is if we take, say, B to be the negation of B to be equal to the statement A and some other statement D. Okay, so so B is false implies that A and A must be true and some other statement D must be true. Okay. Okay, so if we take this definition of B, then B times A times B is clearly equal to A times D, because say this would be A and B, so this is just equal to B. Okay? And now, what is instead B? Well, B is the negation of AD, which is essentially A plus D. Okay, so what does this mean? So this means that the negation of AD means that neither A nor D occur, which is exactly this statement here, that neither A nor B occur. Okay? Or say that yes. Yes. Let's think about this. I mean, this is so the so this is the event that A and D occur, and this is the complementary of that event, which is not the event that neither A nor B occur, which would be this. So this is different from this, and indeed this is the event that so the negation of A, in order for these to be false, you need either A to be false or D to be false, okay, which is exactly equal to this, okay. Okay, so then this means that A times B is equal to A times A plus D. So and this is clearly equal to A, because if A and A plus D must be true, then this is the same statement as saying that A, sorry, must be false, that A should be false. This only occurs if A is false. This statement is true only if A is false. Okay. Then, if you apply these two relations to this equation here, you will get that gamma of AC times S of, now here you have, this is B S of gamma of BC divided by gamma of A and C. This must be equal to gamma of B and C times S of gamma of A and B and C divided by S of B, gamma of B given C. Okay, so just rewritten this this equation where this S of gamma of A and C is just gamma of not A given C, and because not A and B is equal to not A. So you see that we find, if we call this X, gamma of AC, we call it X, and this we call it Y, then we find an equation for this function S that is a functional equation that tells you that X times S of S of Y divided by X must be equal to Y times S of X divided by y. Okay. So this is an equation that should be satisfied for each x and y in 0, 1. And so let's see, for example, that it is consistent with these two limits here. Because, say, if you take y is equal to 1, what you get is that x times s of 0, this should be 0, because s of 1 is equal to 0, divided by x is 0. So this is equal to s of x. Okay, so with s of 0 equal to 1, this means that if you apply, so if you apply s twice to x, then you get x. So this is what you expect, because you think that this function gamma applied to the negation of a statement should be the same as the function gamma applied to the statement itself. Okay. Okay, so now what is the general solution of this equation? Well, the proof is again a little bit lengthy, but you can check easily that the function s of x, which is 1 minus x to the m to the power 1 over m, with m a positive real number, satisfies this equation. Okay, so you can check it as an exercise, but for any x and y between 0 and 1, then this is satisfied. Okay, so then what does this mean? Well, it means now that if you take the function gamma of a times b raised to the power n, then this satisfies the following relation, that gamma of the negation of a statement given b is equal to 1 minus gamma of that statement given b to the power n, not just because of this equation. Okay. So now, if you define this as the probability, if you define the probability of a statement or a negation of a statement as this function gamma raised to the power m, then this function here satisfies both the product rule and this sum rule. And starting from this, you can essentially compute this function p for any combination of events. And essentially these are the rules of probability, so that now you can define this as the probability. So you define the probability of a statement A given a certain state of knowledge B as this function gamma, which is, we remind you, is a function W of the plausibility of a statement AB raised to the power m. Okay, so this tells you that no matter how you define your plausibility, among statement, as long as it satisfies these conditions of common sense and consistency, etc., etc., then you can find a function w and an exponent m such that there is this that you can define this function here, which is the probability that satisfies these two rules. Okay. So to state it differently, you can show that the rules of probability can be derived by just an extension of logic to how you would like a robot or an intelligent being to compute probability, to compute the plausibility of statements, quantify the plausibility of statement in a consistent manner. Okay. And so this I hope that gives you a little bit more a sense of what is the meaning of probability. Notice that in this definition of probability, you never need to define what is the sample space. You never need to define a priori what is the set of all possible statements that you can talk about. So, in some sense, this is a more general definition of probability, and the one given by the Kolmogorov axioms is a special case, or is contained in this. But in order to make calculations, in many cases, it is convenient to think in terms of the Kolmogorov axioms, because then you can be sure about, say, how you are defining probability, what is your sample space, etc., etc. So in this sense, Kolmogorov axioms are a useful scheme, or say discipline. Okay, allows you to discipline the way you think about probability, that you compute probability.